This is example 8 on page 92 of the workbook that we're looking at. And this is going to be our first example of using the limit comparison test to determine whether a series converges or diverges. Okay, so if you look at part A here, you might recognize this series as being the same series that we looked at back in example 7. Okay, since the limit comparison test is a little bit more involved than other tests that we've used, I like to start by doing a little bit of scratch work. All right, so we will start with the term in the series that we were given, 1 over 2 to the n minus 1, and the idea of the limit comparison test is to find a nicer series that's somehow similar to this one. Okay, and generally what you do to find that nicer series is to think about dominant terms. Okay, so in the numerator, we've just got one term and it's a 1, so we'll keep that. And in the denominator, we've got a 2 to the n minus 1. Which of those two terms is dominant? Which is the important one? Well, it's going to be the 2 to the n, since that goes off to infinity. Okay, so far, what we've determined are what we generally call the bn and the an. Okay, if you look back at the limit comparison test, there were two series, the series bn and the series an. Okay, and then what we're hoping is that we can look at the an and determine whether it converges or not. Okay, and we already made this observation in example 7, that the series 1 over 2 to the n is a geometric series that converges. Okay, our reason for that was that it had a common ratio of 1/2, which was less than 1. Okay, the next part of the limit comparison test was we needed to take a limit of the ratio of bn over an. Okay, now here the algebra is going to get a little bit involved, okay, because bn and an are both fractions, so bn looks like 1 over 2 to the n minus 1, and we're dividing that by an, which looks like 1 over 2 to the n. Okay, since we're dividing two fractions, we can multiply by the reciprocal, and so this becomes the limit as n goes to infinity of 1 over 2 to the n minus 1 times the reciprocal of 1 over 2 to the n, okay, which is 2 to the n over 1. Okay, let's rewrite that into one fraction. So if we multiply those two fractions together, this becomes 2 to the n over 2 to the n minus 1. There's the limit that we need to calculate. Okay, and you might notice that that limit has the form infinity over infinity. Okay, so we're going to use L'Hopital's rule on it. Okay, and taking the derivative of 2 to the n, that's a formula that you probably have not seen for a really long time in Calculus 1. You can take the derivative of 2 to the n, but to do that we need to use the following derivative formula. Okay, the derivative of 2 to the x is 2 to the x ln of 2. This is a Calculus 1 derivative formula. Okay, you may need to look back, maybe in your Calculus 1 notes to find that. Okay, but that is how you take the derivative of 2 to the x. And so what we're going to get is in the top, oh whoops, we are using n's, not x's. Our derivative in the top is going to be 2 to the n ln of 2. Okay, there's that derivative using that formula. And in the bottom, we've got another 2 to the n, so we're going to get a 2 to the n ln of 2. And then the derivative of minus 1 is just 0. That goes away. All right, well, notice what happens here. After taking those derivatives, we've got the same thing in the numerator and the denominator. Those cancel, and we're just going to get 1 out of that. Okay, and so that number 1 is what we called the value of c. Okay, if you look back at the language of the limit comparison test and notice that that c is positive and finite. Those were the two properties that we wanted it to have. Okay, So we have all of the pieces that we need to do the limit comparison test here. Okay, the last step is to actually write the proof. Okay, and just to warn you, this is going to be a longer proof because there are more pieces to the limit comparison test. All right, so what's important here? Well, one thing is that the c that we calculated is positive and finite, so let's start there with our proof. Okay, so since c equals 1 is positive and finite, the other thing that was important was that the series an, okay, up here, that was a convergent series. We kind of looked at it, noticed that it was geometric, and then concluded that it was convergent. Okay, so that's our next observation. Is a convergent geometric series because of the fact that R was a half. If we put those two facts together, we can conclude that the series that we were given, 1 over 2 to the n minus 1, also converges. Okay, and so that proof is our answer. Okay, and you can see that's more complicated than the previous convergence tests that we've used. Okay, so it'll take a little getting used to. Okay, the good thing here though is that every time you use the limit comparison test, your proof is going to kind of sound similar to this one. They're always going to be kind of the same pieces. You're going to start by making this observation about your c. The next step is going to be making a statement about the series that you're comparing to, and then you're going to conclude with whether or not the series